Great, thank you. Great pleasure for me to introduce the second ESR project. I apologize. I wish I was there in Padova. I got lucky a few years ago. I could visit for a mini sabbatical, and I can confirm this is a very lively city. So the title of our ESR project is very long. It's called Experimental and Computational Investigation of Cyanobacteria Culture using far-red, near-infrared light for oxygenic photosynthesis and nitrogen fixation. I will try to demystify this title for you in a moment. But if you go to the next slide, I will start by introducing our team. So the most important element is the ESR. It's Giovanni. I understand there'll be an ESR presentation after the early career researchers. So I'll quickly, but Giovanni graduated from Padova, so I have no doubt that he's happy to be back there and spend some time. Giovanni is also lucky because he doesn't have 1, 2, or 3 supervisors. He has 4 supervisors. So 3 of them, Bill Rutherford, the lead supervisor, Andrea Fantuzzi, and Stefania Viola, are in the Department of Life Sciences at Imperial College, and they specialize in biochemistry and bioenergetics of photosynthesis. And the 4th supervisor is myself. I am with the Department of Chemical Engineering, and I work on mathematical modeling and process optimization. So our goal is to mix these expertise, so very much in the spirit of digitalization. So let me, if you go to the next slide now, I will try to discuss a bit more about what we have in mind for this ESR project. The background for the project, you can see it on the left of the slide, is that a few years ago, it was discovered that certain cyanobacteria can grow in near-infrared lights, and they are exposed to near-infrared lights. The standard chlorophyll A systems shut down, and different systems containing chlorophyll F turn on instead. And what my colleagues at Imperial College showed is that the chlorophyll F, in fact, happens to play a key role in photosynthesis under shaded conditions, and it is using this low energy infrared light to do the complex biochemistry. So that was very exciting. And what we are trying to do is, in Giovanni's project, is to try and develop a better understanding of all the processes that are taking place under these conditions. So of course, we aim to study the growth under infrared light of those cyanobacteria, but we also aim to study the transition from chlorophyll A to chlorophyll F, which turns out to be fairly slow, whereas the reverse conversion back to chlorophyll A happens to be very fast. So there will be some experimentation conducted that combines proteomics, transcriptomics, but also fluorometry to develop a better understanding of what is going on here. And in parallel to these experimental efforts, we will try to embed the current and the new knowledge into mathematical models. For instance, by building on existing models we have of photosynthesis in visible light and try to extend them to near infrared light. And the idea is also for these models to be able to guide the experimentation, so not only one way, but going the other way around. And eventually to be able to help improve culture conditions under for long wavelength species. Thank you. I think I'll stop here.
Thank you, Benoit.